Welcome back. In this video, we will look at example problems of finding the center of mass and centroids. Let's get to it. All right, so here's our first example. We want to find the center of mass for the following point masses on the x-axis. And so here we have four masses and their respective placements with respect to the x-axis. And so if we draw that x-axis, this is going to be our axis, and then I'll label the origin x equals 0. We can place each of these masses along this axis. And so let's start with mass 1. We have m sub 1 is equal to 7, and then its x value, x sub 1, is equal to negative 3. So if this right here is negative 3 along our x-axis, then our mass, m sub 1, will be right here. So that is m sub 1. Then our second mass, m sub 2, is equal to 4, and that mass is located at x sub 2, which is equal to negative 2. And so if this is x equals negative 2, then our mass m sub 2 will be right here. All right, so that's m sub 2. And then for our third mass, m sub 3, that's equal to 3, and it is located at the x value of 5, right? X sub 3 is equal to 5. And so if this is x equals 5, then our mass, m sub 3, will be located right here. So that is m sub 3. Then for our last mass, m sub 4, that is equal to 8, and it's located at x equals 4, right? Because x sub 4 equals 4. And so if this is x equals 4, then our mass, m sub 4, will be right here. All right, and so if you imagine that this x-axis is a seesaw where the fulcrum is at the origin, when we are determining the center of mass, we are looking for a placement along the x-axis such that the seesaw is balanced, meaning that it would not rotate to one side or the other. And so in order to find the center of mass, x bar, we need to add up all of the moments for each of our masses and then divide by the total mass of the system. And that will look like this. X bar is equal to the sum of the moments. So we'll have m sub 1 times x sub 1 plus m sub 2 times x sub 2 plus m sub 3 times x sub 3 plus m sub 4 times x sub 4. And that will be divided by the sum of the masses, so we have m sub 1 plus m sub 2 plus m sub 3 plus m sub 4. Right, so remember that a moment for a mass is equal to the value of that mass times the distance from the axis of rotation. And so we're adding up the moment for each of our masses individually, and we are dividing by the total mass of the system. And so that calculation will look like this. We'll start with the moment for the first mass, so we'll have m sub 1 times x sub 1, so 7 times negative 3, so we'll have 7 times negative 3, plus the moment for our second mass, so m sub 2 times x sub 2, which will be 4 times negative 2, so we have 4 times negative 2, then we'll add that to the moment for our third mass, and m sub 3 is equal to 3, and x sub 3 is equal to 5, so we'll have 3 times 5, so I'll write 3 times 5, plus the moment for our fourth mass, which will be m sub 4 times x sub 4. So we'll have 8 times 4, and so I'll write that down, 8 times 4. All right, and then that will be divided by all of our masses added together, so we will have 7 plus 4 plus 3 plus 8, since those are the values of all our masses. So we have 7 plus 4 plus 3 plus 8. Okay, and so if we simplify, 7 times negative 3 is negative 21, so this is equal to negative 21. And then we have 4 times negative 2, so that's negative 8, so we'll have minus 8. Then we will add 3 times 5, which is 15, so we'll have 15, plus 8 times 4, which is 32. So we have 32. And that will be divided by all of these masses added together, and 7 plus 4 plus 3 plus 8 is equal to 22. So we have 22 in the denominator. All right, and so if I clean up my work a little bit, we can simplify this. Negative 21 minus 8 will be negative 29. So this is equal to negative 29 plus 15 plus 32 is 47. And so we'll have 47, and that will be divided by 22. Now, negative 29 plus 47 is equal to positive 18. So this is equal to 18 divided by 22. And that can be reduced by a factor of 2 in the numerator and denominator, and so this is equal to 9/11ths. And so the center of mass for this system of masses along the x-axis is 9/11ths. And that's a little bit less than 1. And so if this is x equals 1 on our x-axis, then our center of mass will be located right about here. And so that is x bar, which is where we would want to place the fulcrum in order to balance this seesaw so that it does not rotate about the axis. Okay, let's look at a different example. Alright, so here's our next example. We want to find the center of mass of the given system of point masses. And so we're given this table here, where the top row has the measurement of our masses, and then the bottom row has the coordinate points where these masses are located in an xy plane. Right, so in this case, each of our point masses has an x coordinate and a y coordinate. And so let's graph these on a coordinate plane. I'll start by drawing the y-axis, and then I'll draw the x-axis, and then I'll label it. So this is the y, and this is the x. And then let's plot each of our masses on this coordinate plane. So we know that m1 is equal to 10, and that it's located at the point 1, negative 1. And so if this is x equals 1, and this is y equals negative 1, then our point mass m1 will be located right here on our coordinate plane. So that is m1. Then for our next mass, from this table we can see that m sub 2 will be equal to 2, and that is located at 5, 5. And so if this is x equals 5, and this is y equals 5, then our point mass m sub 2 will be located right here on the coordinate plane. So that is m sub 2. And then from this table we can see that we have one more mass. We have m sub 3, and that is equal to 5, and that is located at negative 4, 0. And so if this is x equals negative 4, then our point mass m sub 3 will be located right there along the x-axis at negative 4. Okay, so that is m sub 3. And so when we're trying to find the center of mass for this system, we are trying to find a point on the xy plane such that it is balanced for all 3 point masses. And so since we are working in a two-dimensional system, unlike the previous example where we had a one-dimensional system, the center of mass will have both an x-coordinate and a y-coordinate. And we represent that with x bar, y bar. All right, and x bar will be equal to the moment for each mass along the y-axis, which will be equal to m sub 1 times x sub 1 plus m sub 2 times x sub 2 plus m sub 3 times x sub 3 divided by the sum of the masses. So we have m sub 1 plus m sub 2 plus m sub 3. All right, and so if we plug in all of our values, x bar will be equal to m1, which is equal to 10, times its x-coordinate, x sub 1, so that will be 1 from this coordinate point. 1 is the x-coordinate, so we have 10 times 1 plus m sub 2, which is equal to 2, times its x-coordinate, which is 5. So we have 2 times 5 plus m sub 3 times its x-coordinate, and so we'll have 5 times negative 4. So we have 5 times negative 4, and that will be divided by the sum of the masses, and so we'll have 10 plus 2 plus 5. And so I'll have 10 plus 2 plus 5 in the denominator. All right, and so if I clean up my work, we can simplify, and so this will be equal to 10 times 1, which is equal to 10, plus 2 times 5, which is also equal to 10, so we have plus 10, and then we're going to be adding 5 times negative 4, which is equal to negative 20. So we will subtract 20. And then we will divide by the denominator of 10 plus 2 plus 5, which will be 17. Okay, and so in the numerator here, we have 10 plus 10, that's equal to 20, and then minus 20 is equal to 0. So this is equal to 0 divided by 17, and 0 divided by anything but 0 is going to be equal to 0, and so that's just equal to 0, which means that x bar, the x-coordinate of the center of mass, is equal to 0. All right, and so if I clean up my work, we now know that x bar is equal to 0, and so now we need to find y bar to complete our center of mass. Now y bar is going to be equal to the sum of the moments for our masses about the x-axis divided by the total mass of the system. And so that will look like this. We'll have m sub 1 times y sub 1 plus m sub 2 times y sub 2 plus m sub 3 times y sub 3. And that will be divided by the total mass of the system, which is m sub 1 plus m sub 2 plus m sub 3. Okay, and so let's plug in all these values. This is going to be equal to m sub 1 times its y-coordinate, y sub 1. So we'll have 10 times negative 1. So I'll write that, 10 times negative 1, plus m sub 2 times y sub 2. And m sub 2 is equal to 2, and its y-coordinate is 5. So we'll have 2 times 5. So we'll write 2 times 5 plus m sub 3 times y sub 3, and m sub 3 is equal to 5, and its y-coordinate is 0, so we will have 5 times 0. So we'll have 5 times 0, and then divide that by the sum of our masses, which will be 10 plus 2 plus 5, and so I'll write that in the denominator. We'll have 10 plus 2 plus 5. Okay, and so if I clean up my work, we can simplify, and this will be equal to 10 times negative 1, that will be negative 10, plus 2 times 5, that's equal to positive 10, and then we will add 5 times 0, which is just equal to 0. And that will be divided by 10 plus 2 plus 5, which is equal to 17. And so then negative 10 plus 10 is 0 plus 0 is still 0, and so this is equal to 0 divided by 17, which just like x bar is going to be equal to 0. And so what we find here is that the center of mass for this system is going to be the origin, right? So if I clean up my work here, we have found that x bar is equal to 0 and y bar is equal to 0, which means that our center of mass, x bar comma y bar, is equal to 0 comma 0, which is the origin of our system. And so this point at the origin, 0, 0, is the center of mass for this given system. So here's our next example. We want to find the center of mass of the lamina bounded by y equals the square root of x equals 1, and y equals 0 with a uniform density rho is equal to 2. Okay, and so if we want to find the center of mass for a lamina that is a region on the xy plane, we need to know the formulas associated with calculating that center of mass. And so I went over these formulas in my lesson video, but I thought it would be good to review them here before we start going through the example problem. And so if we want to find the center of mass of our lamina, which is a coordinate point x bar comma y bar, we need to know how to calculate each of those coordinates. And so x bar is equal to the moment about the y-axis divided by the mass of the lamina, and y bar is equal to the moment about the x-axis divided by the mass of the lamina. Now the mass of the lamina, which we need for both of these calculations, is equal to this definite integral right here. We have the density, which is represented with the Greek letter rho, times the definite integral that represents the area of the region or the lamina that we want to find the center of mass for. And so that's just an integral from a to b of f of x minus g of x, where f of x is the top function of the region and g of x is the bottom function. And then our bounds of integration are just the two values of x for which the region lies between. Now for the moments, we need the moment about the y-axis and the moment about the x-axis. These are also two separate definite integrals that we need to know. The moment about the y-axis is equal to the density times the integral from a to b of x times the difference between our two functions, f of x and g of x. Then the moment about the x-axis is equal to the density times the integral from a to b of 1/2 times f of x squared minus g of x squared. Okay, and so you're going to want to know all of these formulas when you are working on finding the center of mass of a planar lamina like we are in our example problem. One more thing to note though is that because the calculation for the centers of mass involves dividing each of the moments by the mass of the lamina, notice that both the mass and the moment formulas have a common factor of the density of the lamina. And so because of that, that density is just going to cancel out in the division process when calculating the centers of mass. And so because of that, the center of mass is not dependent on density, just the shape of our lamina. And so we can ignore the density given to us in our problem and just assume that the density is equal to 1 and completely omit that rho from our formulas. It'll save us a little bit of time and we won't have to worry about multiplying everything by 2, only to then divide it back out. Okay, so just because our problem tells us that rho is equal to 2, we can actually ignore that and pretend that it's equal to 1. And so let's go back to our example problem. Let's start by drawing the region that is bounded by these equations, which represents the lamina whose center of mass we want to find. And so here's the y-axis, and then here's the x-axis, and then I'll label them. So this is the y, and this is the x. And then let's graph each of our equations. Let's start with y equals the square root of x. We know that the square root of x is just half of a parabola that points in the positive x direction. So this is y equals the square root of x. And then we have x equals 1, which if I make this right here, x equals 1, then our line for x equals 1 will look something like this. Okay, so this line is x equals 1. And then finally we have y equals 0, but that's just the x-axis, right? That is where y is equal to 0. And so now we can see that the region bounded by those graphs is this region right in here. That will represent our lamina. And so I'll shade that in real quickly. We want to find the center of mass for this region, or lamina, in this problem. All right, and so let's start by calculating the mass of our lamina. We know that the mass is equal to rho times the integral from a to b of f of x minus g of x times dx. And this is just the area of this region. And so what is the top function f of x of our region with respect to x? Well, if we look from the top down, the top of our region is y equals the square root of x, and the bottom of our region is y equals 0. And so y equals the square root of x is f of x, and then g of x is just going to be equal to 0. Okay, and so then the only other thing that we need to determine are the bounds of integration. And those are the two values of x that our region lies between. And so it lies between x equals 0 and x equals 1. All right, and so this will be pretty simple to set up. Remember that we can ignore the density here. It doesn't matter that it has a uniform density of 2. We can just assume that it's 1 because that 2 is going to be divided out anyway when we calculate the center of mass. So the mass is equal to the integral from 0 to 1 of f of x, which is the square root of x, minus g of x, which is 0, times dx. And so this is just equal to the integral from 0 to 1 of the square root of x times dx. Okay, and so we can rewrite the square root of x to be x to the 1/2 power, and by doing that, we can more easily see how to use the power rule of integration. And so if we use that rule, we'll add 1 to the exponent and then divide by that new exponent. So this will be equal to x to the 3/2 power, because 1/2 plus 1 is 3/2, divided by 3/2, and that will be evaluated from 0 to 1. And so if I clean up my work here, remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so this will be equal to 2/3 times x to the 3/2 power evaluated from 0 to 1. And so now we can evaluate this at 1 and subtract the evaluation at 0. So this will be equal to 2/3 times 1 to the 3/2 power minus 0, because if you plug 0 into this expression, you're just going to get 0. Okay, and so this is equal to 2/3 times 1, because 1 to the power of anything is just 1, and so this is equal to 2/3. The mass of our lamina is equal to 2/3. Okay, and so if I clean up my work here, I put our mass value down here. Remember that the mass of the lamina is 2/3, and now we can start to calculate our moments about each axis. And so let's start with the y-axis. The moment about the y-axis will be equal to rho times the integral from a to b of x times f of x minus g of x. And that will be multiplied by dx. All right, and so let's set this up. This will be equal to rho, but we can ignore that, just like we ignored it when we calculated the mass. It's just going to divide out anyway when we calculate the center of mass. And so we'll have the integral from 0 to 1, right? The same bounds of integration that we used for the mass integral, because our region still lies between x equals 0 and x equals 1. And so then we'll have x times f of x, which is the square root of x, minus g of x, which is 0, times dx. And so if we simplify, this is equal to the integral from 0 to 1 of x times the square root of x, which is x to the 1/2 power, times dx. And then if we multiply x times x to the 1/2 power, we add the exponents, so 1 plus 1/2 is equal to 3/2, and so this is equal to the integral from 0 to 1 of x to the 3/2 power times dx. Okay, and so if I clean up my work, we can solve this integral by using the power rule of integration. So we'll add 1 to the exponent and divide by that new exponent. So this is equal to x to the 5/2 power divided by 5/2 evaluated from 0 to 1. And so once again, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so this is equal to 2/5 times x to the 5/2 power evaluated from 0 to 1. And so now we can evaluate this at 1 and subtract the evaluation at 0. And this will be equal to 2/5 times 1 to the 5/2 power minus 0, because once again, plugging 0 into this expression is just going to produce 0. All right, and then 1 to the 5/2 power is just 1, so we have 1 times 2/5, which is equal to 2/5. And so now we found that the moment about the y-axis is equal to 2/5. Okay, so I'll clean up my work here. Remember to keep a note of what your moment about the y-axis is. I have it down here. And now let's calculate our moment about the x-axis. And so we'll have that the moment about the x-axis is equal to rho times the integral from a to b of 1/2 times f of x squared minus g of x squared times dx. All right, and so if we plug in everything we know, and that includes ignoring the density, once again, it's just going to be divided out when we calculate the center of mass. And so this will be equal to the integral from 0 to 1. We keep the same bounds because our region still lies between x equals 0 and x equals 1. And then we'll have 1/2 times f of x squared. So we'll have the square root of x squared minus g of x squared, which will be 0 squared times dx. All right, and so if we simplify, I'm going to pull this 1/2 to the outside of the integral. So this is equal to 1/2 times the integral from 0 to 1 of the square root of x squared. That's just going to be equal to x because the square root and the square will cancel each other out. So we have x minus 0 times dx, but that's the same as just x dx, and so I'll write x dx. And so now we have a very simple integral that we know how to solve by using the power rule of integration. And so I'll add 1 to the exponent and divide by the new exponent to have that this is equal to 1/2 times x squared divided by 2, and evaluate that from 0 to 1. And so if I clean up my work here, this will be equal to 1/2 times 1 squared divided by 2 minus 0 squared divided by 2, and that will be equal to 1/2 times 1/2 minus 0, which is equal to 1/4. Okay? And so the moment about the x-axis for our lamina is equal to 1/4. And so if I clean up my work again, we now have calculated everything we need to find the center of mass of our lamina. And so we need to calculate each coordinate of the center of mass. And so x bar is equal to the moment about the y-axis divided by the mass, and y bar is equal to the moment about the x-axis divided by the mass. And so let's start with x bar. That will be equal to the moment about the y-axis, which is 2/5, divided by the mass, which is 2/3. And remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So this is equal to 2/5 times 3/2, and those 2's will cancel out, which leaves us with an answer of 3/5. And so 3/5 is the x-coordinate for our center of mass, but then let's calculate the y-coordinate, or y bar. We're going to divide the moment about the x-axis by the mass, and so this is equal to 1/4 divided by 2/3. And once again, we can multiply by the reciprocal of 2/3, and this will be equal to 1/4 times 3/2, which is equal to 3/8. And so 3/8 is the y-coordinate, which means that the center of mass, x bar, comma y bar, is equal to 3/5, comma 3/8. That is the center of mass for the lamina in this example problem. Let's look at one more example problem for this video. All right, so here's our last example. We want to find the centroid of the region bounded by the graphs of y equals x squared and y equals 6 minus x. All right, and so find the centroid is just another way of saying find the center of mass for the region bounded by these graphs. Centroid and center of mass are essentially the same thing. And so let's start by graphing the region bounded by these two equations. So I'll draw the y-axis, and then I'll draw the x-axis, and then I'll label them. So this is the y, and this is the x. And then let's graph each of our equations. And so let's start with y equals 6 minus x. We know that negative x is a line that passes through the origin with a slope of -1, but this 6 tells us to shift that up 6 units in the y direction. And so if this is y equals 6 right here, then our line will look something like this. All right, so that is going to be y equals 6 minus x. Then our other equation is y equals x squared, and x squared is just a parabola that points upwards, and the vertex is at the origin. And so that parabola will look something like this. That is going to be y equals x squared. And so now you can see that the region bounded by these two functions is this region right in here. And so I'll shade that region in. We want to find the centroid, or the center of mass, for this region right here on our coordinate plane. Okay, and so let's start by calculating the mass of our region. And the mass is equal to the density times the area, which is the integral from a to b, of f of x minus g of x times dx. Now we need to figure out a couple things before we are ready to set up this definite integral. We need to know the top function of our region, f of x, and the bottom function of our region, g of x. And so if we look at our region from the top down, this line right here, 6 minus x, that's the top function. And so 6 minus x will be f of x. And then the bottom function is the parabola. And so y equals x squared will be g of x. All right, and then we also need to know our bounds of integration, which are the two values of x that our region lies between, and currently we don't know what that is. We need to know the x values of the intersection points for these two functions. And so in order to find those x values, we need to set our two functions equal to each other and solve for x. And so if we do that, x squared is equal to 6 minus x, and then if we add x to both sides of the equation and subtract 6, we will have x squared plus x minus 6 is equal to 0, and then we have a quadratic that we can factor. And since the x squared term has a coefficient of 1, all we have to do to factor this is ask ourselves what two factors of our last term added together will get us the coefficient of the middle term. And so to get negative 6, we can multiply positive 3 and negative 2, and positive 3 plus negative 2 is positive 1. And so our factorization will be x plus 3 times x minus 2, and that will be equal to 0. And so we can set each of these factors equal to 0 and find the x values of the intersection points of our two graphs. So we'll have x plus 3 is equal to 0 and x minus 2 is equal to 0, which tells us that x equals negative 3 and x equals positive 2. Okay, so our two functions are going to intersect at x equals negative 3 and x equals positive 2, which are the two values of x that our region lies between. And so right here is x equals 2, so that's one intersection point, and then right here is x equals negative 3, and that is the location of our second intersection point. All right, and so now we can set up our definite integral. We will have that the mass is equal to the density. Now in this case, we're working with a region, and so we are allowed to assume that that density is just equal to 1, and so we can ignore that. We're just multiplying 1 by the area, and so then we will have the integral from negative 3 to 2, right? Those are the values of x that our region lies between, of f of x, which is 6 minus x minus g of x, which is x squared, times dx. Okay, and so now we can integrate each of these terms. So this will be equal to 6x minus x squared divided by 2 minus x cubed divided by 3. And that is evaluated from negative 3 to 2. Okay, so the integral of 6, which is a constant, is just equal to that constant times the variable of integration, which is x. So we have 6x as the integral. And then we use the power rule of integration on these two terms. We added 1 to the exponents and then divided by those new exponents. Okay, and so now we can evaluate this at 2 and subtract the evaluation at negative 3. So this is equal to 6 times 2 minus 2 squared divided by 2 minus 2 cubed divided by 3 minus 6 times negative 3 minus negative 3 squared divided by 2 minus negative 3 cubed divided by 3. And so if we simplify, this is equal to 12 minus 4 divided by 2, which is just equal to 2. So we'll have minus 2. And then we will subtract 2 cubed divided by 3, which is 8 thirds, minus 6 times negative 3 is negative 18, minus negative 3 squared, which is 9, divided by 2, minus negative 3 cubed, which is negative 27 divided by 3. And then if I clean up my work, we can simplify further. 12 minus 2 is equal to 10. So this is equal to 10 minus 8 thirds. And then we will subtract these terms. And these two negatives are going to cancel out. And so I'm just going to rewrite this to be plus 27 thirds. But 27 divided by 3 is just 9. So we'll have negative 18 minus 9 halves plus 9. Okay, and then 9 plus negative 18 is negative 9. And so this is equal to 10 minus 8 thirds minus negative 9 minus 9 halves. And then if we distribute this negative through this quantity, we'll have that this is equal to 10 minus 8 thirds plus 9 halves. And then if we add all of these terms together, we will have that the mass is equal to 125/6. All right, and so that is the mass of our region. And so if I clean up my work here, I have our mass value down here for us to reference later, but now we can start calculating the moments about each axis. And so let's start with the moment about the y-axis. And that is equal to the density times the integral from a to b of x times f of x minus g of x. And that's multiplied by dx. All right, and so if we set this up, remember that we can ignore the density. We're assuming that it's equal to 1. So this is equal to the integral from -3 to 2, right? Those are the bounds of integration because those are the two values of x that our region lies between that did not change from the previous integral. And then we have x times f of x minus g of x, and f of x is 6 minus x, and g of x is x squared. So we will subtract x squared and multiply by dx. All right, and so if I distribute this x through this quantity, this will be equal to the integral from -3 to 2 of 6x minus x squared minus x cubed times dx. And now once again, we can integrate each of these terms by using the power rule of integration. And so we'll have that this is equal to 6x squared divided by 2 minus x cubed divided by 3 minus x to the 4th power divided by 4 evaluated from -3 to 2. Now 6 divided by 2 is equal to 3, so we can simplify this to be 3x squared. So I'll rewrite that, and we will have 3 times x squared. Okay, and so now if I clean up my work here, we can evaluate this expression at 2 and subtract the evaluation at -3. And so this is equal to 3 times 2 squared minus 2 cubed divided by 3 minus 2 to the 4th power divided by 4 minus 3 times -3 squared minus -3 cubed divided by 3 minus -3 to the 4th power divided by 4. All right, and so now if we simplify, this is equal to 3 times 2 squared, and 2 squared is 4, so 3 times 4 is 12, so we'll have 12 minus 2 cubed divided by 3, that's going to be equal to 8/3, minus 2 to the 4th power divided by 4, and 2 to the 4th power is 16, so we have 16 divided by 4, but that's just equal to 4, so I'll rewrite that to be 4, and then we will subtract 3 times -3 squared. -3 squared is 9, and 9 times 3 is 27, so 27 minus -3 cubed divided by 3, and -3 cubed is -27, so we have -27 divided by 3, minus -3 to the 4th power, which is 81 divided by 4. So we have 81 divided by 4. Okay, and so now we can simplify further. We know that 12 minus 4 is equal to 8, so this is equal to 8 minus 8/3 minus 27 plus 27/3, because these two negatives will cancel out to become positive, and then we will subtract 81/4. All right, and so then if we distribute this negative through this quantity, this will be equal to 8 minus 8/3 minus 27 minus 27/3 plus 81/4. And so if I clean up my work here, we can simplify even further. 27 divided by 3 is equal to 9, so this is just -9, so I'll write that as 9. And then -27 minus 9 is equal to -36, and then if we add that to 8, we get -28, and so this is equal to -28 minus 8/3 plus 81/4. And so then if you add all these together, you will find that the moment about the y-axis is equal to -125 divided by 12. Okay, and so that is the moment about the y-axis. And so if I clean up my work here, I have our moment about the y-axis down here, and so now all we need to calculate before we can find our center of mass is the moment about the x-axis. And so the moment about the x-axis is equal to the density times the integral from a to b of 1/2 times f of x squared minus g of x squared times dx. Okay, and so let's plug in everything we know. Once again, we can ignore the density. We're assuming it's equal to 1. And so we'll have that the moment about the x-axis is equal to the integral from -3 to 2. We're using the same bounds of integration once again. They are still the values of x that our region lies between. And then we'll have 1/2 times f of x squared. And f of x is 6 minus x, so we will have 6 minus x squared minus g of x squared, which is x squared, and so we'll have x squared squared times dx. All right, and so if we simplify, I'm going to pull this 1/2 to the outside, so this is equal to 1/2 times the integral from -3 to 2 of 6 minus x squared. Now if we square this quantity, I'm going to use the trick where you square the first term, then multiply the two terms together, and then multiply them by 2, and then add the last term squared. So 6 squared is 36, so we'll have 36, and then we'll multiply 6 times negative x, which is negative 6x, and then multiply that by 2 to get the middle term. So we'll have negative 12x, because 2 times negative 6 is negative 12, and then we will add the last term squared, and negative x squared is x squared. So we will have x squared, and then we will subtract x squared squared, which is x to the 4th power, if we multiply those exponents, and so we will have x to the 4th power times dx. Okay, and so now we can integrate each of these terms, and so we'll have that this is equal to 1/2 times 36x minus 12x squared divided by 2 plus x cubed divided by 3 minus x to the 5th power divided by 5, evaluated from -3 to 2. Okay, so we use the power rule of integration on these last 3 terms by adding 1 to each exponent and then dividing them by their new exponents. And then for 36, 36 is just a constant, and so the integral is just going to be that constant, 36, times the variable of integration, which is x. Okay, and so if I clean up my work here, 12 divided by 2 is equal to 6, and so this term will be negative 6x squared, so we'll have 6x squared. And now we can evaluate each of these terms at 2 and subtract the evaluation at -3. And so we'll have that this is equal to 1/2 times 36 times 2 minus 6 times 2 squared plus 2 cubed divided by 3 minus 2 to the 5th power divided by 5 minus 36 times -3 minus 6 times -3 squared plus -3 cubed divided by 3. And then I ran out of space, so I'm going to write the next term below here. We're going to subtract -3 to the 5th power divided by 5, and then that's it. All right, and so if we simplify, this will be equal to 1/2 times 36 times 2, which is 72. So we'll have 72 minus 6 times 2 squared. 2 squared is 4, and 4 times 6 is 24. So we have minus 24 plus 2 cubed divided by 3. So we have 8/3 minus 2 to the 5th power divided by 5. And 2 to the 5th power is 32. So we'll have 32 divided by 5. And then I'm going to write the rest of these terms beneath here. So I'm going to have minus 36 times -3. And that's equal to -108 minus 6 times -3 squared. -3 squared is 9, times 6 is 54. So we have minus 54 plus -3 cubed divided by 3. That will be -27 divided by 3. And then we will subtract -3 to the 5th power divided by 5. And -3 to the 5th power is -243. And that's still divided by 5. And then that's it. All right, and so to simplify further, this is equal to 1/2 times 72 minus 24. That's equal to 48. So we'll have 48 plus 8/3 minus 32/5 minus -108 minus 54. That's equal to -162. And then we'll add -27 divided by 3. But -27 divided by 3 is just -9. So we have -9 and then minus -243/5, which those two negatives will cancel, and so we have plus 243/5. All right, and so if I clean up my work here, we can simplify further. So this is equal to 1/2 times 48 plus 8/3 minus 32/5. And then if we distribute this negative through this quantity, we'll have plus 162 plus 9 minus 243/5. Okay? Now 48 plus 162 plus 9 will combine to be 219. So this is equal to 1/2 times 219. plus 8 thirds minus 32 fifths minus 243 fifths, but we can combine those two fractions since they have the same denominator. And so negative 32 and negative 243 will combine to be negative 275. So I'll rewrite this to be 275 divided by 5. And 275 is divisible by 5. And so if you divide, that's just equal to 55. So we have minus 55. And then 219 minus 55 is equal to 164. So this is equal to 1/2 times 164 plus 8 thirds. And 164 plus 8 thirds is equal to 500 thirds. And so this is equal to 1/2 times 500 thirds, which is equal to 500 sixths, which we can reduce by a common factor of 2 in the numerator and the denominator to get a final answer that the moment about the x-axis is equal to 250 thirds. Okay, and so if I clean up my work here, we now have all three values that we need to calculate the centroid for this region. And so remember, the centroid, or the center of mass, is a coordinate point x bar comma y bar, where x bar is equal to the moment about the y-axis divided by the mass, and y bar is equal to the moment about the x-axis divided by the mass. And so let's start with x bar. If we plug in our values, we know that the moment about the y-axis is equal to negative 125 divided by 12. And so this is equal to negative 125 divided by 12 divided by the mass, which is 125 sixths. So I'll have 125 sixths. But remember, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so this is equal to negative 125 twelfths times 6 divided by 125. Now the 125 in the numerator and the denominator will cancel out. And so this is equal to negative 6 twelfths, which reduces to negative 1/2. And so x bar is equal to negative 1/2. And so far our centroid will be negative 1/2. And then let's find the y coordinate, which is y bar. So if I clean up my work here, y bar is equal to the moment about the x-axis divided by the mass. And the moment about the x-axis is 250 divided by 3. So we have that this is equal to 250 thirds divided by the mass, which is 125 sixths. And then once again, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so this is equal to 250 thirds times 6 divided by 125. Now 250 divided by 125 is 2, and 6 divided by 3 is also 2. And so this is equal to 2 times 2, which is equal to 4. And so y bar is equal to 4, which means that the y coordinate for the centroid, or the center of mass, is 4. And so negative 1/2 comma 4 is the centroid, or the center of mass, for this region bounded by x squared and 6 minus x. All right, and with that, this was the last example for this video. And so if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. And so I will see you next time.